Today I'm going to show you what's inside the ignition system and how it works to power your car's engine. Now every gasoline engine requires air, fuel, and spark to create combustion to turn the crankshaft. Now that air will go through the air intake system, I've got another video on that, and head into the air intake manifold over here. The air will then make its way down into the engine head where it will combine with fuel from the fuel injectors in a port injected engine, and then the ignition coil will drive the spark plug down in the engine to create combustion to move the piston down. All of these components in the ignition and fuel system are electronically controlled through the ECU, which takes readings from various other sensors in the system to determine when and how combustion occurs. So we're going to start here by removing the fuel rail and the intake manifold from this engine. Next up we have the ignition coils, and there's 6 of them on this V6 engine, 3 on each bank. Now the ignition coils are called a coil on plug system, where the coil is directly related to the plug. There's no central coil in the system, and they're all electronically controlled through the ECU because there's no distributor in this system. And now I'm going to pop off this engine head here so we can have a closer look at the valves and the spark plugs underneath. So here we have an overall system diagram of how the fuel and ignition system works relative to the ECU controlling the engine. We start here with the air and fuel that goes into the engine here, that's controlled through the throttle body and the fuel injectors respectively. The spark timing is also controlled through the ignition coils by the ECU, and then combustion occurs. Now the output of the engine is measured by the camshaft and crankshaft position sensor, as well as the oxygen sensors. That's all fed back to the ECU. In the meanwhile, the ECU is also looking for different inputs to the accelerator pedal from the driver to keep this one big closed loop control system. Now the fuel injector takes fuel from the fuel rail here and sprays it into the air intake port on the intake plenum before it goes into the cylinder. This is called multi-point fuel injection, and that's because the fuel can be controlled into each cylinder individually, as opposed to having it mixed in a carburetor up above and then shoved down the throat of the engine. Now the purpose of the fuel injector is to atomize any fuel that comes in from the high pressure side on the fuel rail here and spray it out the nozzle where it can mix with the air before going into the engine. Now the spray pattern of the fuel injector is actually controlled by the design of these 4 little holes at the top of the injector here. Now on the engine head, this here is where the fuel injector would mount, and it would spray directly into the airstream going into the engine to the 2 individual valves per cylinder. The 2 main types of injection are port and direct injection, with direct injection spraying high pressure fuel directly into the combustion chamber. This is more fuel efficient because it allows the fuel to swirl better with the air inside of the combustion, and you also don't have to wait on the intake valve to open to bring in a rich mixture. Port injection, on the other hand, is a little bit more cost effective, and it helps to clean out the air intake valve so you don't get carbon buildup. And you can see how on the top where the fuel injector has been mounted, the gasoline's cleaned off all the carbon deposits compared to the bottom. Now the fuel injector is controlled by the ECU through these 2 pins here, and when you apply 12 volts it activates the solenoid inside of here to allow the gasoline to flow through with a reaction time in milliseconds. Each one of these fuel injectors are powered by 12 volts from the fuse box and are grounded through the ECU in order to activate it. Now if the fuel injectors are all clogged up due to bad gas or carbon deposits, that could cause incorrect stoichiometric ratios and an increased emissions output from the engine because the engine is burning too lean. Now if you've got a leaky fuel injector, either through the O-ring here or the actual pintle valve inside is busted, that could cause increased fuel consumption because fuel is just dripping down. Now to keep your fuel injectors clean, you can run good gas through it as well as some fuel injector cleaner, or you can take them for an ultrasonic bath. Here's a quick cross section of the fuel injector. We have the electrical connector that connects to this coil here and the pintle rod inside, which forms an electromagnet. Now when activated, the pintle rod will move back, and that will allow gasoline to flow through the injector, past the ball valve, and out through the nozzle. Now I'm going to cut open this fuel injector to see what's inside. And I'll just remove this tip here. So the pintle valve here is what's responsible for moving when the solenoid inside activates it. Now I'm going to cut open the body of the fuel injector. Now taking a closer look at this injector here, you can see that we have this steel center tube here where the gasoline flows from the high pressure side here out to the pintle valve here. We have 2 distinct coil wires here that come from the 2 leads fed by the ECU, and that coils around this steel core here. And here's a closer look at the coil here. Any coil, through the principle of electromagnetism, that's wrapped around a steel core will create an electromagnet, and that's what causes this little pintle valve to suck in when the electromagnet is activated. Now the fuel system is governed by this closed loop control system here, with the ECU sending an injection pulse over to the injectors. It then gets burned through combustion in the engine, where the oxygen sensor or the air fuel sensor will sense the stoichiometric ratio of the air to the fuel. Now ideally this ratio should be 14.7 parts air to 1 part of gasoline, Anything that is above that becomes a very lean mixture, and anything that's below that becomes a very rich mixture. So this closed loop system is always working to try to optimize the stoichiometric ratio for a complete combustion. Now the AF sensor also senses fuel trim, the short term of which is what governs this closed loop control system here, and is the instantaneous value of the fuel mixture at that existing time. Now the long-term fuel trim is averaged out over a longer period of time and is used to determine if there's any issues with the engine, such as a vacuum leak, and to throw a check engine light. Now at the bottom of the head here we have these two air intake valves that open up to bring in an air fuel mixture into the combustion area. We have the spark plug that ignites it and the two valves for the exhaust. Now we all remember how the 4-stroke engine cycle works. We have air and fuel that suck through the intake stroke here. It's then compressed, the spark fires, causing combustion, which pushes the piston down, turning the crankshaft, and then finally the exhaust is escaped through the exhaust valve. Now with the fuel system covered, we're next going to take a look at the ignition system to see how it fires the spark plug. Now at the top of the coil pack we have a 3-pin connector, 12 volts, ground, and a switching wire. We have the step-up transformer in the head here, and then we have a long electrode that's really well insulated to take those thousands of volts and fire the spark plug way down inside of the engine head. Alright, we're just going to loosen up the spark plug here and just pull it out. Now that's quite an oily spark plug due to bad tube seals, so I'm just going to come in here with my brother's old underwear and wipe that up. The spark plug would normally sit inside of the ignition coil here, so we can take those thousands of volts into the center electrode to the gap at the tip. Now the basics of how an ignition coil works is we've got a primary coil, an iron core, and then a secondary coil that has many more turns than the primary coil. Now when 12 volts is applied, there's an electromagnetic field that is formed here, which induces a small voltage in the secondary coil, not enough to fire the spark plug. However, when the switch is switched on and off, that causes a very rapid change in the electromagnetic field, which induces a huge voltage in the secondary coil, which is enough to spark the spark plug. Now the ECU is basically the switch for any modern ignition coil system. Now it's separated through a power transistor over here, and that turns on and off the circuit very rapidly on the primary side, which induces that extra voltage on the secondary side to fire the spark plug. We've also got a condenser to protect the primary coil from any voltage spikes. Now the spark plug has an electrode that's typically copper and runs along its length that's connected to the ignition coil on this side. We have these threads here that are grounded out against the engine head when they're threaded in, and that leads over to this finger here that sits over the tip. Now we have some insulation at the bottom here, and more importantly there's insulation in between the tip here and the grounded section of the thread. Now the more the insulation, the colder the plug is going to run because the heat cannot dissipate fast enough from the spark plug. Now in typical daily driving, you're going to want a little bit of a hotter plug to burn off any carbon deposits and make the plug last a little bit longer. Now some premium spark plugs have a coating of platinum or iridium on the copper tip here, and that's to help it last longer so it doesn't burn out from arcing. If you got a lot of soot buildup or your spark plugs are worn out or the gap is messed up, well, the spark's not going to fire very cleanly, and then you're going to have a misfire issue and your engine's not going to run very efficiently, so it's important to keep these up to date. So here we have a cross section of a spark plug here. You can see the center electrode runs right through to the spark plug gap, and then we have this white insulating material that separates it from the ground on the outside. So we're going to start taking apart this ignition coil to see what's inside. Now the rubber on this just seals it against weather and waste spark from exiting out, and that's pretty much what touches the spark plug inside of the boot. Now we're going to cut open this ignition coil to see what's inside. Just going to remove the top there and have a look at what's inside. Now that was quite dusty, so I'm just going to come in with my wife's old shirt here and just dust everything off. Now the top here, you can see the start of the circuit where these leads here come into the main ignition coil. It's going to come in with my wife's old charcoal toothbrush here. It's not dirty, it's actually charcoal, highly recommended by her, and wipe this off. We've also got a power transistor in here. From the side here you can see the thin sheets that are stacked up to form this iron core here. At the top here you can see the primary coil on the outside, which doesn't have as many turns and is a much thicker wire compared to the inside coil here, which is a thinner wire, has more turns. Now that difference is what allows the primary 12 volt wire to convert into many thousands of volts when the switch is switched to fire the spark plug. Now I'm going to chop off the bottom. And if I remove that, you can see the coil inside of here. Looking at the coil from the side, you can see that this coil is actually coiled sideways around this way and not in the same plane as the spark plug itself. If you look at the back here, you can see the primary coils over here and the secondary coils, which I haven't quite grinded through yet, completed at the back here. So essentially it goes in a circle like that. I'm just going to start taking apart this coil here. See the individual plates coming apart here, and here's what the center of it looks like. This center piece here is actually a magnet, and that's pretty much the end of this ignition coil. We have this outside horseshoe piece that is a bunch of layers, and the inside piece here, with the coils around it. Now I'm going to section the spark plug. And you can see what's inside of the spark plug. We have the insulation here and the electrode, which has a platinum tip on it. And then you have the body of the spark plug here, which has that center electrode that runs all the way down to the tip here to carry the voltage down to the tip. Now we're going to have a look underneath this valve cover. Now underneath the valve cover we have the intake and the exhaust cams. Now the timing system largely takes care of controlling when the valves are to open and to close to allow air to go in or exhaust to escape. However, the computer, which is controlling the ignition and the fuel, needs to know when to inject and when to put a spark in, and that's where we turn our attention over to the cam position sensor on the side of the head over here. Now the camshaft position sensor is responsible for telling the computer where this camshaft is in the combustion cycle and how fast it's running, and therefore which valves are open and which valves are closed for each cylinder. Now the cam position sensor is actually a Hall effect sensor that senses the position of these notches on the camshaft. So if we take a look at some of the readings from the ECU here, the camshaft position sensor is going to tell the ECU where the top dead center position of the piston is through that missing tooth, and just before that it's going to fire the spark plug in order to allow combustion to occur and for it to expand during the combustion stroke, enabling maximum amount of power. Now shortly before that, the ECU is going to fire the fuel injector for a very small period of time if the RPMs are low. However, when the throttle position sensor opens up here, the camshaft position sensor is going to tell the ECU that the RPMs are increasing and to elongate the pulse width of the fuel injector signal to put more fuel into the cylinder. It's also going to advance the ignition timing to bring the spark further back from top dead center because the fuel is going to take the same amount of time to burn. Now in a typical 4-stroke cycle, you want the spark plug to fire just as the piston is moving in to compress the air-fuel mixture. The fuel mixture is going to take a little bit of time to spark, ignite, and start expanding, and by that time the piston is almost on its way to its downstroke, so the maximum amount of work can be applied to this piston with the full force of combustion. Now at higher RPM, you have to advance the timing of the spark plug a little bit more because the piston is moving a lot faster, but the fuel still takes the same amount of time to combust. Now on the other hand, the ECU can retard timing of the spark plug so it sparks on its downstroke to reduce fuel consumption and emission. Now the ECU has a fixed table of values built in for the ignition timing and the fuel injector pulse width based on the recommended fuel and optimal combustion for this engine. So for example, looking at this graph here, we have the mass airflow reading here and the RPM. So for a particular airflow value and RPM, it's going to give you a particular fuel pulse width. Similarly for the ignition, a particular mass airflow and an RPM will relate to an amount of time that the ECU needs to advance the timing before top dead center in order to allow for optimal combustion. Now the ECU can also vary the opening of this valve relative to the piston using variable valve timing, but we're going to talk about that in another video. Now the order in which the ECU fires the ignition coils and the spark plug for each cylinder is called the firing order. Now, the firing order is dependent on the position of this piston relative to the crankshaft, and it's different for each piston. So for example, if this is piston 1, 2, 3, 4, 5, and 6, the firing order might be very similar, 1, 2, 3, 4, 5, and 6. And it's done this way for three main reasons. The first of which is heat dissipation. If you have cylinders that fire at the same time near the same bank, this bank is going to heat up and the cooling system can't take care of it. The second reason is of course the exhaust gases. Again, if you have a lot of exhaust gases building up on one bank, you're going to have a lot of pulsation and irregularities in the exhaust manifold. And the third one of course is vibration. If you have cylinders on the same side moving up and down, the engine is not going to be that balanced compared if you had to move them on the opposite side where they kind of cancel each other out. So from the ignition coils to the spark plugs and the fuel injectors, these are all the components that are required to make the ignition system and fuel system work on your car. We're also going to give big thanks to the ECU for being able to control and think of all this really quickly. We couldn't do it without you on a modern car. Make sure you follow me on Instagram for more behind the scenes footage and subscribe for more videos just like this one.